Morning all.
Morning, Doug.
Morning.
Brandon is here, Connor's here, Hannah's here. Are you guys the ones that don't struggle to be up and rolling by 8? Or are you just like disciplined and you're like time people? 8 means 8.
Time person for sure.
I guess that's a pretty interesting distinction. I think some people are conscious of time and some people aren't, and they've actually both have strengths.
Well, I'm a time person, but COVID has really tested me. I think that it's kind of easier to show up in class in person than it is to log on to Zoom. And it's Zoom. If you're 10 minutes late, it doesn't feel like as big of a deal.
Yeah, it's true. I've noticed being a teacher, it's kind of interesting because it sort of feels normal to me in the sense that I'm talking and I'm looking at you guys. But then I attend a meeting where I'm sort of in your shoes and I feel the same way. It's kind of like, oh, cool. I can just kind of pay attention, get up, go to the bathroom, get up, go to the refrigerator, get some food, just kind of pop in and pop out, not as accountable, which is good and bad.
Yeah, I thought it was good at first, and then it really started testing me later on.
Yeah, I'm enjoying the breakfast during lecture.
Yeah, exactly. Yeah, you can leave your camera off and just be all messed up and have chow sticking out of your mouth, and that's kind of nice. Let's see. Let me get up. I want to say one quick thing about the project. That I hope you took away from it. I just went in and looked to see who turned things in, and it looks like most of you got something turned in, but I haven't looked at any of them yet.
Doug, did you get my email that
Yeah.
for some reason my project was too big? I don't know why.
Yeah, I did. I saw that note just a few minutes ago, so I didn't look at my email yet, but I'm sure I got it. So
okay, it was a little nerve-wracking, like not turning anything into my open app.
Let's see. Was that yesterday? Let me take a quick look just since you brought it up. Why not look?
Yeah, I think it was yesterday around 1 p.m. or noon.
I might have been kayaking. I see Hannah in there. That's good. Yeah, Connor, I see you too.
Awesome, thank you.
All right, we're good. Welcome all. Today we are solving second order homogeneous linear differential equations. So you can tell people what you studied today. Weird. But before we do that, I want to say one quick takeaway from the project that I was very anxious that you get. And I'm hoping that between your discussions with other people and your own thinking that this happened. And I'm just going to use the kind of example that I gave as the project as my illustration. So let's see the equation. Let's see, and you took a test, all kinds of stuff. Anyway, you got your test, I graded it, gave that back. Before I forget to say something about it, I'm always very anxious because as I said, I mean, it probably took me literally 6 hours to grade your tests, and there's only like, 12 of you. So I really try to figure out where you went wrong and why, and I make the questions worth enough points, like 8 points, some of the classic solve differential equations questions, so that I only had to take off a point or two if you did something wrong. Excuse me, so it still kind of preserves your grade. But kidding aside, I really I would always like you to feel free to discuss / argue for points. Because I'm all about, do you understand this stuff? And if you do, and kind of can explain your thinking, and maybe, either number one, you're not sure that I saw it correctly, Worst case scenario, I say, no, I think that's fair. I think you should lose 2 points for that. And then, nothing is lost. But I really would invite you to do that, just because I like to know your mind on those things. Because as I said, I do put a lot of thought into it. And I sort of want to minimize the damage for kind of little mistakes as opposed to important mistakes. And so please stay after class and let's talk about that. So let's take a look at this one. Let's solve it traditionally. And I want to see if you can take away the one big thing. So dy dx equals x squared minus y, or you could say that dy dx, if I add y to the other side, equals x squared. And so this is actually solvable. And that's kind of what I asked you to do, is to, in red here, is to find a bunch of solvable differential equations and then investigate, that, what I was calling that asymptotic curve, kind of the curve around. It's almost like it divides the curve into two different curves, if you will, two types. So, well, this one's solvable, so let's solve it. So notice our P is 1. So that means if I multiplied both sides by e to the integral of 1 with respect to x in this case, since it's dy dx, then that'd be e to the x. And so that's what I would need to multiply both sides by. So if I multiply both sides by e to the x, Connor, you notice what I just did there? What did I just do there, Connor? What did I just multiply by e to the x?
You multiply it, you figure out your y.
Yeah.
Oh, no,
For some reason you spazzed out on the test, I just remember. And I know you know that.
Yeah, I messed up distributable and it actually ruined like a lot of my tests, made it really hard.
Yeah, you did a whole bunch of, you made it really hard and etc. So anyway, that's an example of what I'm talking about. It's not like you don't know that. You probably looked at that and went, God, what was I doing?
Yeah, that was pretty rough.
So this now takes the form of the product rule. Notice the derivative of e to the x is e to the x. And so, okay, that really works. So if I took e to the x times y and took the derivative of it, that'd be the same as the left side. The right side I will leave alone. I'm going to do this kind of fast. And so I need to take the integral of both sides. The integral will get rid of the left side's derivative, fundamental theorem of calculus. And the integral of the right side is going to take us a little bit of time, because I would need this to be u and this to be v prime. And if I did that, integration by parts says that would be the same thing as u times v. Since u is x squared, then that means u prime would be 2x. And v, the integral of e to the x, is also e to the x. So integration by parts says u times v minus the integral of u prime times v. So we say to ourselves, is that an easy integral? And the answer is, well, it's going the right direction, but I still can't do it because there's still two things. So if I move this 2 out front, just to ignore it for later, and then I kind of start over and call this u and call this v prime, then that would mean u is equal to 1 finally, sorry, u prime. And v, the integral of e to the x, is still e to the x. And so now my integral becomes, let's see, e x to the y equals, I have x squared e to the x, that's this, minus 2. And now what do I have instead? I'm replacing now this. So integration by parts says I can't do the integral of x times e to the x. Well, what can I do instead? Well, I can do u times v, which is x times e to the x, which I don't have to take the integral of, minus the integral of u prime, which is 1 times v. And so finally, and I'm being lazy and not writing dx there, but finally I have an integral I can actually take. And so I end up with e to the x y equals x squared e to the x minus 2x e to the x. And then finally, the integral of e to the x is e to the x, but I have a minus 2 and a minus So it becomes plus 2e to the x. And I took the integral, so that's plus c. So now I can solve for y. I've got my answer now. If I divide by e to the x, that's really convenient because it cancels here, and it cancels there, and it cancels there. And so it's a parabola. Well, it's a parabola if you forget that c, which is very important that you do not forget. And so that's the general solution. You should feel relatively good about that, although you got to be good at integration by parts to follow that as quickly as I just did it. But I just found the solution for that. And so and I just showed you that out of interest. What I'm really interested in here is like, what's this direction field that I get up here? And what's that curve that's in it? And so basically what I'm noticing in this, as far as this, what I was calling this auxiliary curve, which I gave my own symbol for, is basically any point you pick below it, it kind of starts curving down here, but then it turns away and goes this way. Whereas up here, it kind of turns and goes kind of over here. It sort of exits the stage right. So kind of down below this dividing curve A bar, you sort of have what looks like a cubic equation, whereas up here, it looks like kind of a squared equation. And so again, the issue that I was trying to get across to you is it's just all of these problems seem to have kind of this dividing line above which they kind of look like one thing and then below which they look like something else. And I was very anxious for you to kind of discover what that connection really is. And so watch this in action. This is the main thing that I wanted you to take away from this. So if I go into Desmos now, I stuck this in Desmos before class, there's the equation that I just found, x squared minus 2x plus 2 plus c over e to the x. And so notice down here, I'm getting these cubic equations, and then it kind of pops up, and now all of a sudden it kind of looks like a parabola. And so the question is, where's the dividing line? I'm just playing right now, but notice how it's like, oh, I'm below it. Oh, looks like I'm above it. I'm below it. I'm above it. What do you notice about C over there that defines where I'm above and below it? Notice it's hopping from positive. Notice I'm at positive 0.1 now, and when it pops to negative 0.1, it suddenly looks like the cubic version. And so it actually looks like when C is 0, that's the dividing line. And that's the one thing I really wanted you to get. Notice if C does go away, then this term up here goes away, and that actually is a parabola. It didn't just look like a parabola, it is one. It's x squared minus 2x plus 2. Whereas that's if C is 0. But then if you go above that, now all of a sudden C is a number, and then it's got an e to the x term. And so notice it's not as obvious, but it's not a parabola now. So it kind of looks like a parabola, but it isn't one. But notice it has an e to the x term. Well, if that C is positive, you get one type of graph. If that C is negative, you get another type of graph. And so it turns out that that's how you find what I'm calling the asymptotic curve. Did you discover that? If C is 0, that's the division. If C is above that, positive, you get one sort of looking graph. And if C is below that, you get another looking graph. And in the end, you always end up with, some kind of a term over here with the y, like we had an e to the x over there, and then you divide it away. And so that's what makes that C term go from a constant to being a real contributor to the way this graph looks. When C is 0, notice this doesn't have an e to the x term at all. There isn't one. Whereas if C isn't 0, it does have an e to the x term. So now you got a parabola plus an e to the x. And you might notice that, if I wanted to, I could have written it as C times e raised to the negative x, and that would have accomplished the same thing. So in this case, the asymptotic curve really is a parabola. It's the parabola, it's the difference between the two. It's the dividing line. Above it, you get one type of graph. Below it, you get another type of graph. Did you discover that?
Yes.
Yep.
Cool. And then, whatever else you might have noticed is great, but that's the main kind of thing I wanted you to take away from it. You get these just crazy graphs, and at first instinct, it's just, we get really, surprising graphs that we would never recognize as we kind of sketch all of the, as we slide the C around, we just think, what a weird looking direction field, if you will, this creates. And yet there really does come from one equation. So anyway, it's kind of interesting. So I'll take a look at that and then we'll have a conversation about that if necessary. Okay. So now what do we are going into chapter 4, the second part of this class. We're already a third of the way done. And we are studying in 4.2, second order. Does that mean anything to you? We briefly discussed that language. Homogenous. That does not mean anything to you, except for like milk. Linear, that means something to you. Differential equations. So second order linear differential equation should mean something to you, but maybe not homogeneous just yet. Weird. What in the world is that? Well, I want to introduce this to you quickly by just showing you one of the applications that's going to be the guiding force for a whole bunch of this kind of second midterm. And that has to do with the application of a spring. And this is going to blow your mind. It's such a powerful idea in physics. I remember not connecting super well with physics, both in high school and college, because I never really kind of had it explained to me in a way that kind of took it to the next level. But the way you need to think of a spring is not literally just a spring, although this models that, but basically anything that kind of vibrates to a stop. If you hit a table, it's going to kind of bounce to a stop. If you think about a skyscraper in a city, kind of blowing in the wind, it wobbles back and forth. Anything that kind of has a vibratory sort of a motion, the suspension in a car has a vibratory motion to it. Have you seen that Tacoma Narrows Bridge, which is an awesome engineering failure where the bridge just starts wobbling back and forth in the wind and eventually falls apart? Anything that kind of wobbles back and forth, a tree blowing in the wind. If you push on a tree, if the wind pushes on it and then stops, the tree is going to kind of wobble back to a stop. And so it models anything in motion that kind of has that effect. It isn't just a spring, even though the book will make it look that way. And I want to introduce this, like where a second order comes from, like where that would come up in the world, and remind you what second order means if you don't have a picture in your mind. So let's take a spring, and I'm just going to use an actual spring here. And let's say it kind of was here, but then you pulled it out. So now it's actually here, and we're going to say that distance is y. So I pulled it further, and this is at rest. This is where it was at rest. And so we pulled it out a certain distance. Well, you may know Newton's second law. Some physics for you. Newton's second law, which actually says that force equals mass times acceleration. Which is just an unbelievably ubiquitous equation. It's just amazing how much it shows up. The entire, I guess, Ben and Landon would know this recently, but the entire second term of engineering is really based around this equation. It's dynamics. We study statics and dynamics, but dynamics is stuff in motion. And force being equal to mass times acceleration is a huge one. Well, you should know that acceleration is the change of velocity, and that the change of position is velocity, and the change of position is velocity. And so really A can be thought of as a second derivative. In this case, we would say that like this, dy dt squared. Or you might just say y double prime, and that's another way to say it. So the point is, go ahead.
Isn't it d squared y over dt squared.
Yep, you're exactly right. I put that first squared. Thank you for correcting me there. That's in the wrong spot. So it's basically saying the second derivative of y with respect to t. So that is what second order means. We've been studying first order equations, which means there's only one derivative in them. But now we're going to study second order equations where there's actually two derivatives. You got to take the derivative twice. And it's really Newton's law and its acceleration that makes this happen. And so does it make sense? That's a force. That's kind of a force on the spring. So force is mass times acceleration. So that's involved in the spring. And then there's also a couple of other things to consider. One of them is the force exerted. This might feel right to you. I hope it does. The force exerted by the spring turns out to be proportional to y. Notice up here, y is the distance you pulled it away from equilibrium. In other words, it's happy when it's at rest. But basically, the further you pull it away from that, the more force is required. And doesn't that feel right? I mean, even just think about, you know, there's a tree, maybe you've been in the forest and you push on a tree. If you push just a little bit, no problem. But the further you push it, the harder it gets to push it over because it wants to spring back to its equilibrium position. Or the same would be true for a spring. If I pull on it a little bit, well, it doesn't take a lot of force to pull it a little bit, but the further I pull it, the harder I've got to pull because it's just trying harder and harder and harder to kind of get it back. Ultimately, if you've had physics, maybe this has, you've seen this before, but ultimately this is something called Hooke's law. I don't remember any of the history on that. Was it somebody named Hooke that discovered that, measured it, so to speak? And that is oftentimes shown like this. How would you write that down? The force exerted by the spring, force of spring is, that's an equal sign, proportional to y. How do I write proportional to y? What does it mean for two things to be proportional to each other?
They've got a proportionality constant.
Yeah, either those two things divided by each other is a constant, or you could just multiply the y over to this side. Usually that's distinguished with a k, but it doesn't really matter. It's just some constant. That's what it means to be proportional. And then, of course, those would be going in opposite directions. In other words, this negative sign right here that I'm adding to this would would point out that if you pull y to the right, if you pull the spring further out to the right, then the force would actually be pushing back this way. Does that make sense? So they're in opposite directions. If y is positive, then the force will be negative. And it'd be true the other direction too. If I pushed the spring tighter in this direction, then the force would actually go back to the right. So it's always trying to go in the opposite direction. This isn't something you don't have to know this for anything in particular, but we are going to be solving problems like this. And so I'd really like you to have a feel for it. And of course, in my opinion, the whole reason you're taking this class is, one, to pass it so you can get where you're going, but ultimately to be able to use it for something. And this is kind of neat. And one of my projects, we're going to play with this and see if we can actually find some things that behave spring-like and try to put numbers to this and see if we can kind of go, wow, yeah, that actually does model it, or maybe not. We need better tools or something like that. So that's a force that's involved. Secondly, there is a force due to friction, force of friction. Turns out that the force of friction is proportional to the speed. And this might make sense to you. If you put your hand out the window of a car, you've all played that game, right? You stick your hand out the window of a car and it's kind of fun to like slide along. Well, if you're going really slow and you put your hand out the window, it isn't pushing that hard on you, right? But if you speed up the car, it becomes harder and harder to kind of control that. And if you go really fast, it's actually kind of hard to put your hand out the window at all without it just shooting back behind you. And so that's kind of what's going on here. I mean, if you think of pulling something out and it, you know, kind of flying back, friction is going to be a force on it. Now it might sort of feel to you, and you know, maybe the picture that I drew, that friction would be a pretty small force. And I think that's generally true, you know, unless the speed was really big and so forth. But the other thing you want to think about is, again, this isn't just a spring. This is like a building waving back and forth in the wind. And so, you know, depending on the shape of the building, as it waves in the wind, that's going to have an effect on sort of its springiness, if you will. Again, you might think, how do I write that down? Force of friction is proportional to speed. There's another force. How would you write that down? Well, let's say the force of friction is proportional to speed. How am I going to write speed down? I could say V for speed, but how else can I say speed?
Derivative of position.
Change of position. So that's speed. Or dy dt, the change of position. And it's proportional. So again, it needs a k, some kind of a constant. I could give it a different letter this time because we don't really want two speeds. To match your book, in case you read it, I'll use the constant b. Should this be negative? Do they work against each other?
No, because speed is just speed, right?
Think about direction. Like if you stick your hand out the window of the car and your car's sort of going forward, so we'll call forward positive. What direction does your hand go? What direction do you feel the force in?
Yes, they should be opposite.
Yeah, if I pulled it out to the distance that I have it sitting right here and I let it go, then of course it's going to want to go that way, right? It's going to want to go left in this case. Well, isn't friction then going to be sort of pushing this way? So it actually in this case is also opposite. I don't think that's obvious, but I just wanted you to think about it a little bit. So if I'm traveling forwards in my car and I stick my hand out the window, don't I feel the force of the wind on the front of my hand, and my hand wants to go the opposite direction the car is going, if you will, relative to the car. And of course, if I was going backwards really fast and I stuck my hand out the window, wouldn't my hand want to go forward? Like friction wants to push in the opposite direction. Or in physics, you know, or in engineering, we're taking a box and, you know, say it slides down the hill like this. And of course, this is why I didn't connect with physics, because who cares about boxes sliding down hills? I tried to use illustrations like skiers and things of that nature, so something actually slides. But if that's the case and it's sliding down the hill, isn't friction actually pushing in the opposite direction? Isn't it pushing, slowing you down effectively? Friction slowing you down, so it's actually in the opposite direction of travel. I just think that's kind of cool. So I want you to at least have some kind of a, you know, connection to this and so forth. Landon, thank you for posting a video of Tacoma Narrows. That's awesome. That's such a cool, maybe I'll show you that before this is done, because that's kind of awesome. So this is another force that's involved. And so in the end, really, this is what's happening. If you want to know the force, if you'd like to know the forces that are acting on the spring, in other words, you say, hey, so this is kind of the final equation. If I say the force on the spring is equal to, well, it's equal to these two things. It's equal to negative ky because of the spring's force minus by prime. Notice that prime kind of got buried up there. I'm going to darken it in a little bit. Minus b, that's the force. The force is those two things combined. Now, there can be three other external forces. F-O-R-C-E. These would be things like the base moving, or gravity. Gravity actually figures into this too. So maybe I'll just write i.e. gravity. So it's not that that's irrelevant. So if the spring was sort of hanging down, you would think, oh yeah, okay, that makes sense. So there can be other motion involved, just somebody doing something weird, like you have a slinky and you're up there, externally saying, I'm bouncing it, I'm doing something to it, and so forth. So, there can be other external forces. I'll call those force external as a function of time. I'll just call it force. I'll just call it that for now. And then we said this force right here could be replaced with mass times acceleration. And so in the end, that's kind of what we're about to solve right now. Now notice it's kind of cool what this results in. If I actually kind of add these to the other side, in a sense, the spring equation that we will be working with later as an illustration usually is written down like this: m y double prime, I add b y prime to the other side, I add k y to the other side, and then there's some other force that's usually a function of time sitting on the other side. Like this is the spring equation. Notice that all of these are constants. Mass is typically a constant, although if you think about a rocket taking off, burning gas as it goes, maybe its mass isn't a constant. But typically, it's something hanging on a spring. And again, I like to think of it more as like the suspension on my mountain bike or something like that, because it has a springiness to it. But those are all just constants. But do you see that as a second order linear differential equation? What makes it linear technically is the fact that m, b, and k are constants, or that they're functions of time. What we don't want is y's there. But that is a second order linear differential equation. And so that models just a ton of things that exist in the world. Anything that vibrates to a stop is modeled by this equation. So it's such a powerful idea. This is not just a spring that you would play with in a physics class and kind of nowhere else. So as an introduction, I would now like to show you how to solve one of these babies. Oh, and by the way, it's just kind of cool to notice that m, just see this room in my notes and I kind of forgot about it. The m constant has to do with inertia, and b has to do with damping, and k is really the stiffness. That's called the stiffness of the spring. So we're going to investigate all of these things, and it's just remarkable how neat this is. I think as we get into this later on, basically what we need to do now, we can't just play with illustrations like this right now. We just got to be able to solve these things. So we're just going to stop this for a little bit, solve some boring examples, some just practice examples, and then we'll get back to springs and look at how springs vibrate to a stop, and different, how you can actually control all of these things. So you can understand that a huge part of, for instance, in a mountain bike is how the suspension works. Because basically, if you go off of a jump and land, if you just land without suspension, the shock that you get if you land from very high will either hurt you, you won't be able to absorb it, you'll hit your face on the handlebars, whatever. Or if it's too springy, the bike will actually compress down and then it shoots back up in the air and then you fly off the bike and crash, both of which I have done. And so an engineer would spend time with a car or a bike messing with the suspension, trying to design the springiness, if you will, to absorb the impact in such a way as to kind of minimize it. Does it make sense? It's kind of like, the old catching an egg thing where you throw an egg up in the air and you try to, like bring your hands to a stop slowly. I mean, that's what you want, is somebody to like spring down on their mountain bike and then for it to bring them back to equilibrium, because you've obviously compressed the shocks down, to bring them back to equilibrium slowly enough that they don't kind of notice it. And so, how do you do that? So this isn't just, somebody in a physics class playing with a spring. Like, this is an engineer's job in all kinds of aspects in our culture. And you can appreciate I don't know if you've ever seen this online, but it's really fascinating. But when we started making skyscrapers taller, but also we wanted them lighter so that they wouldn't cost as much. They originally were made out of rock effectively, but that's really expensive. And so could we make them lighter? Yeah, we can. But the problem is now all of a sudden wind, and the top stories, people were literally getting motion sickness at the top of the building, because the top of the building might move like 5 feet back and forth, being, hundreds of feet off the ground. And so, what do you do about that? Well, there's this whole design that somebody came up with called a tuned mass damper. Tuned mass damper. You could do a Google search of that, but it really amounts to a giant piece of concrete on the top floor that they can actually control with hydraulics to basically move it in the direction of the wind. In other words, the wind wants to blow the building to my left, and the tuned mass damper, notice the word damper there, the damping effect, that pushes against it in the opposite direction. So it just keeps the building from being able to kind of swing as much. So again, this is a part of engineering. This is not just, playing with springs. It's how to control how stuff vibrates in such a way that it, maybe that's helpful, but in such a way that doesn't actually hurt anything. Hope that makes sense.
That equation's non-homogeneous, right?
Nice. What's homogeneous mean, since you brought it up? If you know.
Are you asking me?
Yeah. You brought it up.
So I think it has to be a linear combination, constants and of derivatives, and then it has to be set equal to 0, right?
Yeah, so for some reason, that's what we're going to start solving right now. I mentioned at the start of today that we are solving second order homogeneous linear differential equations. Well, what's the homogeneous part? I don't know why homogeneous. Homogeneous just means equal to 0. I'm not sure why. Sometimes I get it and sometimes I don't. This is a place that I don't. Why do we need to come up with such a kind of a strange name? Why do we need to come up with a name for this? Is that important? I don't know. I get tired of names at some point. Well,
when I was reading, I think I read, it must have been in chapter 2 for linear, or no, for first order differential equations. They had like another homogeneous form, which is when you could rewrite it as like y over x. And is that the same thing as this? Because it doesn't seem that way. Or why is that homogeneous? Why is that a homogeneous first order differential equation and this is a homogeneous second order, I guess?
The main thing is that it can be written equal to 0. That's all homogeneous means.
Okay.
It doesn't mean it has to be. Like, I could add 5y to both sides and now it's not equal to 0. Does that make it not homogeneous? No. But notice and of course, that y double prime can be written as, and we're just going to think of this as dy dx, not dy dt. But that I could have written it this way. Does that make sense? So we're just practicing. And so the idea is, that's what a spring could be. You notice in front of the y double prime is a 1. And so you could say, oh, it's mass 1. And then in front of the y prime is a b. And so b is -4. So the damping coefficient is -4. And in front of the y is a 5. Well, that's the spring constant. -5 is the spring constant, the stiffness of the spring. And so you can see where this is going. And then notice it has no external forces. It's equal to 0. So this doesn't have any external forces with respect to the equation I just wrote up there. So anyway, that's what mathematicians call homogeneous. And so the question now is if we're just going to practice this, then how in the world would we solve this thing? How could there be? And remember, y is some function of x. Like, y might be e to the x times the sine of 3x or something crazy like that. Remember, that's what we're looking for, is some crazy function of y. I'm going to erase that because it makes it look like that's part of the problem, but that's not. Could be anything. Well, it could be the natural log of the tangent of x or something like that. And so, how are we ever going to find some function that we could take its derivative, multiply it by 4, and then take its derivative again and add all this up and get it to be 0. You might even think even adding derivatives makes no sense. But how am I ever going to find this? And so does it make sense that I'm going to call this an educated guess. And I'm going to show you something later called a Laplace transform that's rather amazing. But right now we're going to have to settle for just an educated guess. Does it make sense that y being an e to the x type of a function would be a good guess? Because first and second derivatives leave it as an e to the x, which would allow me to add it together. Does that make sense? Like normally you can't add functions that you've taken derivatives of. Like for instance, if I said, hey, maybe y is equal to the tangent of x. Okay, well, y prime is the secant squared of x. And y double prime, let's see, that'd be 2 times the secant of x, and then the derivative of secant x is secant tangent. Does it make sense if you needed to add those? They're not going to want to add together because they're not like terms. Does that make sense? So we'll call this a bad guess. You feeling it? So I'm not going to be able to add those, especially if I needed to become equal to a constant or 0 in this case. Like tangent, the guess of tangent of x is not so good. Well, let's go back to that educated guess. Is it e to the x? Well, notice if it was, then that would be equal to y prime and y double prime. And so it'd be very easy, right? Because it's not that hard to take a derivative. And so notice that doesn't work, because if you put that in there, I get e to the x here minus 4 e to the x there minus 5 e to the x there, and I don't get 0. I get negative 8 e to the x, and so it didn't quite work. But what could I do to modify that to make it so that it could potentially work? So you can see why e to the x is, maybe a good idea.
You could put like a constant in front of the x.
Yeah, what if I got kind of a constant involved? Like what if it was maybe y equals a constant times e to the x, or maybe y equals a constant in front of the x itself. Does that make sense?
That's the one I wanted. Second one.
Let's see, would this one help? Notice it has to be the same constant every time. Notice the constant just comes along for the ride. Can you see that the c e to the x actually won't work? Because I'll erase this, but I would get, if I take the second derivative of it, it'd still be c e to the x. If I took the first derivative of it, it would still be c e to the x. If I didn't take the derivative of it at all, it would still be c e to the x. And so notice how that's not going to be equal to 0, no matter what that constant is. Because see, we can't, there's nothing changing it. In other words, I can't change the c in the first, second derivatives. It's just c. And so notice that actually doesn't help. But what about this one? And this is the answer to this question. This could actually work. Let's play with that now. So if that's the case, then we say that y prime, or the first derivative would be r e to the x, e to the rx. And of course, that's chain rule, right? The derivative of e to the junk is e to the junk times the derivative of the junk. The derivative of rx with respect to x is just r. And so that would be y prime. And if I continued with that, remembering r is a constant, so that's kind of important to note. Is a constant. It's not some function of x that we don't know what it is. It's just a constant. So the derivative of r e to the rx, I don't have to do this as a product rule problem, although by the way, you can. but we can just treat r as coming along for the ride. Well, isn't e to the rx still e to the rx, but then the derivative of rx is r, so now there's another r out in front of that. So does it make sense that would be my first and second derivatives? Go into exercise. Have fun. Huh. So let's try this. So if I go back to my original equation, then I say, okay, that was y double prime, which is r squared e to the rx minus 4 times the derivative, which is r e to the rx, and then minus 5 times no derivative at all, which is just e to the rx. So the question is, could I get that to be equal to 0?
If you figure out the right value for r,
Yeah, stare at that for just a second. Notice, what does every term have in common if I want to solve this?
e to the rx.
Every term has an e to the rx in it. So notice if you have junk times junk equals 0, what does that tell you from basic algebra? If you have junk times junk equals 0, what does that tell you?
One of them has to be equal to 0.
Yeah, A or B could be equal to 0, and that would do it. Is e to the rx ever equal to 0?
Nope.
Well, the way I worded it, I kind of answered the question by my tone of voice. A lot of times I do that backwards just to screw people up. But if you graph e to the rx, where r is -1 or r is -2 or r is 3 or 2 or 1 or something like that, remember you get curves that look like this. They come asymptotically down against the x-axis. And so it will never be 0, no matter what you pick for r. Even if you pick r is 0, then you get e to the 0, which is 1. Like, it will never be 0. So that one is not going to produce an answer. Bam. But you know very well that r squared minus 4r minus 5 could be equal to 0 if you choose the right r's. Now, you should have a quadratic formula program in your calculator. We're not wasting any time on this, on solving this by hand. But I made this one up, so I made it really easy. In this case, it factors. If you factor this to r minus 5 and r plus 1, then you discover that r could be 5 or r could be -1. As long as you pick the right r, then this would actually work. Now, in the interest of time, later on when we kind of speed this process up, does it make sense you can actually see that equation even sitting right there? In other words, this is like a 2 and this is like a 1 and then there's a 4 and a 5. Like, do you see that it's like r squared minus 4r minus 5? Like, you could actually see this without even writing everything out. So it's not like I have to, write all of that out every single time. And so this r squared minus 4r minus 5 being equal to 0, this book calls this an auxiliary equation. So when we get better at this, we're just going to immediately stare at this and go, oh, the auxiliary equation for that is r squared minus 4r minus 5. We're going to solve that. And we're going to know that those r's, though, mean something very particular. In other words, those aren't just any old r's. Those r's belong right there. Those r's belong as the constants in an e to the x equation. Does that make sense? So in other words, when I get all solved here and I'm like, yeah, man, r's 5, then we say that means one of my equations is e to the 5x. Does that make sense? That's what the r did.
That's a solution.
That's a solution. Now, I like the way kind of your tone of voice. You're like, what? That's a solution? Well, let's try it out. Let's test it. What's y prime? Well, wouldn't it be 5e to the 5x? And wouldn't y double prime be 25e to the 5x?
Yes.
So let's test it out. So then you're saying if you take the second derivative, which is 25e to the 5x, and you subtract 4 times the first derivative, which is 5e to the 5x, and you subtract 5 times no derivative at all, you're saying that that's actually going to give us 0, really?
Oh, that's pretty cool.
Isn't that cool? So you get 25 e to the 5x minus 20 e to the 5x minus 5 e to the 5x. Oh my God, it actually is 0. Thanks to the constants in front of it. Does that make sense? Isn't that kind of cool?
I guess if you want to solve a differential equation, just multiply it by e to the something all the time.
Yeah, it's kind of interesting, isn't it? So now again, this is very contrived in the sense that this only worked with constants in front of it. In other words, I have a 1, a 4, and a 5 there. I don't have a 5t. Does that make sense? It's like these can get worse, but again, the cool thing is this is what springs do. Those are actually constants. They're not crazy equations and so forth.
Right, that's enough to model it.
But of course, mathematicians always want to say, well, could we do it if that wasn't just a 5? If it was a 5t, or what about the sine of 5t or something like that? Could we still solve these? And so, we're going to wade into that a little bit. But we're solving these with only constant coefficients right now. So just be aware of that. So let's see. We also said then that, so sure enough, that actually worked. That's kind of rad. But then we're also saying that y could be equal to e to the negative x, aren't we? And so if that's true, then y prime would be negative e to the negative x. And then interestingly, y double prime, the negative would pop down front. It'd be back to a positive again, wouldn't it? So let's check to see if that works. So you're saying y double prime, which is e to the negative x, minus 4 times y prime, which is negative e to the negative x. Whoops. And then minus 5 times just y, which was e to the negative x. We're saying question mark. Does that actually work? Does that equal to 0? Do you see that it does? Because you have minus 4 times negative e to the negative x. So you actually have positive e to the negative x plus 4 e to the negative x, a total of 5 of them. And then what do? Well, you go and subtract 5 of them. And so sure enough, check, that is equal to 0. So wow, those are actually solutions. I can't believe it. That's kind of cool. So it's really cool, but it's also a little disappointing because we just guessed, right? We said like, well, maybe it looks like this. And so we found a way, to find an answer. But I also find myself thinking, maybe you do too, like, is there also some sort of weirder answers? Like, could it ever be sine? The derivative of sine is cosine, and the derivative of cosine is negative sine after all. So it's like, there any other kind of functions that would actually work for this? And so that's just kind of interesting to think about. Notice those are particular solutions, though. Remember how we had families of solutions previously? Like with a constant in it? Notice there's no constants in this. Isn't that kind of weird? So there's not a family of solutions to this. It's y equals e to the 5x. You're done. There's no plus c or anything like that. So I guess I kind of have a question here that I'm asking of myself. Like, I wonder if could y equal either e to the 5x plus c? Like, could I put that in there and that would still be a solution? You might notice, and some of you notice this, but if I did do that, wouldn't it be e to the 5x times e to the c, and then I could just call that another c. And so I find myself thinking maybe my guess should just be y equals c e to the 5x. Like, again, question mark, would that work? Like, if I threw a constant in front of that, could that work? Like if it was a certain constant or something like that? Well, let's go try that, because that might be fun. So let's see if that's true, then we would say y prime is 5c e to the 5x, and then y double prime would be equal to 25c e to the 5x. And so let's go plug that back in and see if there's some value for c that we could make that work. So maybe there is a way to sort of throw a constant in this. Now, remember before the constants came automatically because we said we have to take an integral. And when we did that, taking integrals automatically add constants. Whereas here we never took an integral. We just said we're too dumb to take integrals twice. Let's just guess an answer. And we found one that actually worked. So you might think, couldn't I, if I took that original problem, could I take the integral twice somehow, which would bring C's up? And you might think, hey, if there's a second derivative and you take the integral twice, isn't there going to be two constants? So it's like, man, this is really confusing. It's really weird. Well, let's just check and see if this works. So here's my kind of check to see if this will actually work. So our problem was y double prime, which is 25ce to the 5x minus 4 times y prime, which was 5ce to the 5x, and then minus 5 times no derivative at all, right? So the question is there some way I could get that to be equal to 0? What's your thoughts on that? Very important. Think carefully about this.
Well, we just multiplied everything through by a constant. So it is it is the same constant throughout.
Yeah, so anything you put in there would still make it equal to 0. I think.
Are those statements true that a few of your classmates are making?
They're kind of saying what
Notice.
I was thinking, like as long as C is the same throughout, it should be fine.
Yeah, which notice it is, there's no way to have it be different C's, right? Because if I stuck this, if I chose this as my possible answer, then it's the same C all the way through. Notice this is actually true for any C, is I think a couple of you said. So actually there is a C there. We could throw a C there and it wouldn't even matter what it is. Like it could be a 7, a 12, a 19, like you can stick anything in there you want. And so does it make sense that would produce a family of solutions, which is kind of interesting. So you're free to pick any C you want. And that's what happened before, wasn't it? Didn't we say, hey, it can be any C? Well, unless somebody threw an initial value at it, right? If they said, no, it has to go through the 0.01, then that's what allowed us to find a particular solution. So that's actually a more general solution to this problem.
So what you were saying before, when you take two derivatives and get two C's, I guess even if we have the same C, shouldn't the second derivative be a different C? Because it'll be like C squared or something different like that. Like you can combine C's.
Well, no, because if you're saying, what's the integral of x? And so you're going to do it twice. Well, when you took the first integral of x, you would get x squared over 2 plus a C, right?
Right.
But then you have to take the integral again. So what happens when you take the second integral? Well, doesn't the x squared over 2 become x cubed over 6? But what happens to the C? When you take the integral of some constant, what happens?
Oh, do you just add a plus C like 2, C2?
Well, first, what does it do? If that was a plus 7, then what happened? What's the integral of 7?
Just a constant. So x.
No, it's not just a constant. It grows in x, doesn't it?
Yeah.
Isn't the integral of 7x? And then there would be at a further constant. So there's actually two constants that grow and they're different. So two integrals grow two constants. So it sort of feels like if I was able to somehow solve this problem by taking two integrals, it would really grow two constants. Well, do we have two constants?
Not yet,
Two integrals.
but we have two solutions, and the other one could have a different constant.
Yeah, that's exactly right. And so in a sense, we have y1, which is ce to the 5x, but then don't we have a second one that was e to the negative x, and couldn't we give it a different constant? Like those don't have to be the same, do they? So I guess I got to call this constant 1 and constant 2 or something like that. And so this really does have two different constants. And so that's kind of cool. Again, we're just looking for the most general solution we can. So is there anything wrong with just saying the solution is e to the 5x? No, but you don't notice it, but you just sort of said, well, yeah, C is 1. Well, it doesn't have to just be 1. It could be 9 or 12 or anything. So this NEC business here that we just discovered is kind of extremely kind of cool to notice. Not only that, but you could even do this. You could actually just say, and this is actually the ultimate solution. This is the answer, if you will, that would be in the back of the book at this point. In other words, you don't even have to list them separately. You could just list it as one big answer. Now that should bother you a little bit. Like, what do you mean? You can add them and somehow it still works?
Well, it makes sense because you're just multiplying, and then it would distribute, and then you're kind of just like having both solutions in the same equation.
Yeah, I don't know if you're following what David's saying, but just think about what we did a second ago. I don't think I'll write this out, but a second ago, when we did this for the e to the 5x term, didn't it all by itself just produce 0? But because this is a plus sign, not a multiplication sign, wouldn't this one just do the same thing? Like this would make its own 0 and this would make its own 0, and so together they'd be 0. So that's even a more general solution to this, if you will.
So why do you need e to the 5x or e to the negative x? Can't it just be e to the x and then they'll make their own zeros?
Yeah, so there's nothing wrong with, writing them separately. But does it make sense that if you said, for instance, C1, I'm going to make equal to 7, but C2, I'm going to make it equal to 0. Does it make sense that you're saying, oh yeah, well, 7e to the 5x then would be one of your answers. This would be one of your solutions.
I think
So you can produce, just one of them. It's like all solutions have to have both of them. But I'm just saying there's no reason. Mathematicians would say that is WLOG, without loss of generality. Without loss of generality, you could just add them together, because if you pick one of the C's to be 0, then that makes that term gone.
what does that mean without loss of generality?
Just means it doesn't hem you in. It doesn't hurt anything to add them together.
I see.
Basically, then I'm just writing one answer instead of 2. Did that accomplish anything really? Well, not really. But it's kind of cool to just say there's one answer, not 2 now. Before I said, here's the first answer and here's the second answer. Oh, look, there's 2 different answers. And this is saying, well, not really. You could just think of it as one. There's one answer. There it is.
Now
That's kind of cool. How's your brain? Now, one disappointing thing about this is, notice we don't have a way to cheat and look at the slope field for this. Why can't we look at the slope field for this and kind of look at that answer and sort of see if it worked? How did those slope fields work that we found?
We have to have dy dx instead of y on the left side.
Well, we had to have dy dx, not d2y dx. It was like they weren't second orders, right? They were only designed for first orders. You had to be able to rewrite it as dy dx equals, and then equations on the other side. Well, this is a second derivative, and so there isn't an applet or some kind of a program that will sort of let us take a look at this thing.
Is there a method for approximating second order equations?
There is a method for, kind of like Euler's method, where you creep along. We're going to do that a little bit. I forgot what section that's in, but so we are going to be able to produce that. Yeah. Let's see, where is
You
that?
don't have to do that.
It'd be nice not to, wouldn't it? I should not see.
Numerical methods are just hard on the end.
So I think it's important to understand that, or, to point out that this is the general or family solution, general solution, or the family of solutions. So, it's important to understand that this is true for any C1 and C2. And again, the idea there is just they don't have to be the same. C1 could be 5 and C2 could be 9. Like, they don't have to be the same constant. So you get all kinds of graphs, if you will, and I could go into Desmos and, kind of play with that and see what that looked like. And I found myself suddenly thinking, I think I should do that. Just gonna see what that looks like, because I think I kind of know what e to the 5x looks like, but if I add them, what do I get? It just kind of seems fun. So since I can't say C1 and C2, I'm just gonna say A. And of course, it asks me, what constant would you like for that? And I'm saying, I don't know yet. I'll get there later. And then for my second one, I'm going to call it B. B to the negative x raised to the negative x power. And I say I want to add all of those. And so, this is what that equation would look like. And then, of course, it's fun to start kind of dragging these things around. And so notice, again, there's kind of a dividing line. And so you can sort of picture, wouldn't there be a direction field for this? Notice it's real picky. Notice if I pick A to be 0. Notice you just get an e to the negative x graph. Isn't that what e to the negative x looks like? And so, and of course I can still continue to kind of slide this one. So e to the negative x is showing something, working its way. Notice it never makes it to 0. It's approaching the x-axis asymptotically. So it's not 0, but it's getting really close to it. So that's just getting rid of one of them. But if I add the two solutions together, then I get all kinds of, I get again a graph I don't really recognize anymore. So that's just kind of interesting. Kind of looks parabolish right there. So in a sense, that feels like our home turf, just kind of an equation that's made of adding two equations together. That's kind of what we were getting even with first orders, right? A second ago, we had a parabola added to an e. Now we got two e's added together, but they have different coefficients in front of the x. And remember that coefficient when you think of the basic equation, e to the 0.2x, remember that represented 20% growth. And so this is like 500% growth and then negative 100% loss. So, okay, well, that's interesting. Now, would there be a way to find a particular solution? This is a general solution. Sometimes I'll probably get in the habit of putting a little g there just to say this is the general solution. Would there be some way of getting a particular solution to this where C1 is, 7 and C2 is 9 or something like that?
Would need two initial conditions.
Yeah, notice there's two unknowns here. So we'd need some kind of two initial conditions. And so let's do that now. So let's just kind of start over. Let me see if you can solve one of these yourself. Let's look at a second example. So that's a general solution. Let's look at another example now. You solve this one. If I said 6y double prime minus 1y prime minus 12y equals 0, that would be a linear second order homogeneous differential equation. Can you write the auxiliary equation for that and solve it? And then I'll come back and add some initial conditions to it. I'd recommend using the quadratic formula. Like don't spend time thinking about, does this factor, just stick it into the quadratic formula. You should have that in your calculator. Get it in there if you don't. Program quadratic. I would want you to quickly write the auxiliary equation 6r squared minus r minus 12 equals 0, given that we are guessing our equation to be e to the rx. I only did one example to show why that auxiliary equation pops out, but make sure that isn't something you just memorized. Make sure you saw where that came from. That is not magic. You may remember that the quadratic formula can produce really ugly answers. We're going to get into that a little more later in this class, but you could get an answer like 3 plus or minus the square root of 5 over 19 for this. So I'm going to probably work a little harder at that and make sure they come out nicer numbers. Here they come out nicer numbers, but not as nice as last time. Last time they came out as a 5 and a -1. This time though, they came out as 1.5, which I'm going to write as 3/2, and -1.33333, which is actually -4/3. So you should say the general solution for this is C1 e to the 3/2 x plus C2 e to the -4/3 x. Done. There's the general solution to this. Second order linear differential equation produced an auxiliary equation that was squared. And because it's squared, it has two answers. So what if I now add, and please chime in, say something like, slow down, I don't understand what you did here. Like, don't just assume that because nobody's saying anything, everybody's got it but you. Like, speak up. You're paying to be here, get an education.
I just
What
have
if
a question. Is
Please.
YG equal to 0?
I'm sorry,
Like,
say that one more time.
Is
Oh.
yeah, YG, so like is C1 e to the whatever plus C2 e to the junk, is that always equaling 0?
No, it's equal to 0 if you plugged it back into this. If you plug that equation, C e to the 3/2 x plus C2 e to the -4/3 x, if you plugged it back into that original equation, it would be equal to 0.
Would
But
that
it is by itself not equal to 0.
would that equation equal to y, and then you'd have to do y prime and y double prime to it?
Correct, that's right. So we have y, so we only have one thing, we have y, but we don't have y prime. Well, you'd have to take the derivative of it to get y prime, and you'd have to take the second derivative to get y double prime. And early on, I would encourage you to do that. Like go do that on the side and go, oh, look at that, it worked. It really is equal to 0. That's kind of cool.
Got it.
So what if I came back and said y of 0 equals 11/12? So I'm adding these initial conditions. Well, you should say, okay, well, that means if x is 0, y would be 11/12. And so you should say, okay, I can plug that in. So y would be 11/12. That's on the left side. And then x is equal to 0. So wouldn't you have C1 e to the 0 plus C2 e to the 0, thanks to x being 0? Aren't you glad x wasn't like 1? Because if that had been e to the 1 times 3/2, that'd be a lot uglier. So, that's on its way to 1, and that's on its way to 1. So you really have C1 plus C2 equals 11/12. Well, that should kind of bother you. Like, well, isn't there lots of numbers that would do that? Couldn't C1 be 0 and C2 be 11/12? Yeah. Couldn't C1 be 5/12 and C2 be 6/12? Yeah. Couldn't C1 be 97 and then C2, whatever you add to that to get 11/12? So it's like, there's infinitely many answers to this, right? That seems weird. So these problems will have not just an initial location, but even an initial slope. So these initial conditions, like you might say, hey, there's two unknowns there. So it's going to have to be two initial conditions. Well, notice you can't give two initial conditions. I can't say y of 0 is 11/12 and y of 0 is 19. Notice that doesn't make any sense. So your second initial condition might be something like y prime of 0. So there's your first one. And we'll say, in this case, that's equal to, say, 5/12. So what you're being given is an initial location and an initial slope. Now think about that. If you have a second derivative, that's not that surprising, because it's like if I was in a car and I was going somewhere, you'd say, well, you have an initial position, but you also might have an initial speed. I mean, if you're looking at a skier and you say, oh, look at that skier, they're right there. Well, that doesn't mean they're sitting still. They might not be sitting still. Does that make sense? So they have initial position, but they also have an initial speed. So this isn't that weird. If you're talking about something that's got acceleration, if you say, how fast is that skier going? Well, it would sort of depend on where they are and how fast they were going, before gravity began acting on them. So it's not weird that the second initial condition is a slope or a speed. You'd have to know those things. Well, if that's the second condition, notice you actually have to take a derivative now. In other words, you actually have to know the derivative. So I'd have to go find y prime. So C1 e to the 3/2 x. Well, wouldn't that 3/2 come down to be multiplied by the c, and then the derivative of e to the junk is still e to the junk? E to the junk times the derivative of the junk, isn't that the first derivative? And then the same thing would happen for the other one. And again, what you're saying is when x is 0, and so fortunately when x is 0, so the speed is 5/12, but when x is 0, then isn't that just going to leave this 3/2 c1 and 4/3 c2, since e to the 0 is 1 again? So there's your two equations. You have two equations, two unknowns. I'd recommend you use the matrix feature of your calculator for this. But I'll do this one by hand. It's not that hard. Let's see, if I took this second equation here and I multiplied everything in it by 4/3, maybe you can see why I'm doing that. Then I'd have 44. When I multiply 4/3 times 11/12, I'd have 44 over 36. When I multiplied C1 times 4/3, I'd have C1 times 4/3. And when I had C2 times 4/3, I'd have C2 times 4/3. Why did I do that? Because now I can add these two equations together and these C2 terms will drop out. You should be able to do this, obviously by hand, but just cheat. I'm going to type 4/3, 4 divided by 3 plus 3 divided by 2 in my calculator. When I do, it gives me a decimal that I don't recognize, 2.833333. Well, if you go to math and say convert that to a fraction, you get 7/17 C1. Again, you should be able to do that in your head. You should be able to say, I need to multiply this by 2 since the common denominator is 6. I need to multiply this by 3. And so I get 8/6 plus 9/6. All of a sudden I'm realizing I got it wrong. 8 plus, yeah, that's right. 8, 6 plus 9, 6 is 17, 6. And so, but you know, that's just in one more place you can make a mistake. You should consider that, you know, you can do it by hand, but it's like you might make a mistake. And it's also boring. So 44 divided by 36 plus 5 divided by 12. I get some crazy decimal, 1.6388888. I convert that on my calculator to a fraction. It says 59 over 36. So I can divide both sides by 17/6, and even that you could type in your calculator if you want to be lazy. 59 divided by 36, although you got to be careful how you type this, divided by, you'd have to put the second fraction in parentheses, 17 divided by 6. Again, I get some decimal I don't recognize. I say convert it, and I get 59 over 102. The cool thing about your calculator is it actually reduces that for you automatically, which is kind of neat. So, you know, that's not so nice because it came out a really weird number. Now that I know that, of course, you might say, well, I'm going to go back to this equation because it looks easier. I don't want to go to this equation because I'd have to multiply C1 times 3/2, and that's no fun. So over here, I can see all I have to do is take 11/12 and subtract 59 over 102. 11 divided by 12 minus 59 divided by 102. I'm just typing that on my calculator. Again, I get some decimal I don't recognize. So I say math, convert it to a fraction. I get 23 over 68. So C2 would be 23 over 68. So now instead of YG, which was our general solution to this, which I'll go back and sort of highlight back here, I had my general solution. Now I have Y of P, my particular solution, which accounted for my initial conditions. So C1, 59 over 102, and that was C1 was multiplied by E to the 3/2 X, or 1.5X. And C2 was 23 over 68, and it was multiplied by E to the negative 4/3 X. So that's my particular solution. And of course, I could check this because remember, Y of 0 is supposed to be 11/12. So to just double check to make sure I didn't do anything dumb, then if X was 0, then wouldn't that really be 59 over 102 times 1 plus 23 over 68? So in a sense, you might say I'm on the edge of my seat, kind of hoping, question mark, that that actually equals 11/12. So I'm going to check that because I don't trust myself. 59 divided by 102 plus 23 divided by 68. I get some decimal I don't recognize. I convert it to a fraction. Oh, it is 11/12. Cool. So now I can say that's not a question mark anymore. Check. That actually worked. And to even check further, Y prime of 0 was supposed to be equal to, where did it go? 5/12. So isn't the second derivative, you'd have to take the derivative of E to the 3/2 X, which would be E to the 3/2 X, but then you'd have to multiply by 3/2, that 59 over 102. And the same thing with 4/3, you'd end up with negative 4/3 times 23 over 68 times E to the negative 4/3 X. And so if X is 0, this is on its way to 1. That's on its way to 1. So now I'm thinking, I wonder if 3/2 times 59 over 102 minus 4/3 times 23/68. I'm question mark. Is that really equal to 5/12? Again, I'm just going to type that whole mess in my calculator. 3 divided by 2 times 59 divided by 102 minus 4 divided by 3 times 23 divided by 68. I get some crazy decimal. I convert to a fraction. Hey, it's 5/12. That's awesome. It actually checked out. It worked. So now I'm not waiting for the teacher to see if I got this right. If I have an extra few minutes on a test. And of course, it'd be nice on a test if I had made this up so C1 and C2 came out nicer than that, right? Like they came out like 7 and 18 or like whole numbers. But it's like they don't have to. So do you understand the concept between general and particular? Does it make sense to you that this solution here is true for this original equation? It's true for any value you want to stick in there for C1 and C2. Add that back to for any C1 and C2. But as soon as you come back and say, now I'm going to add in these kind of initial conditions, well, now C1 and C2 can't be just anything. You're not going to start out at location 11/12 with speed 5/12 unless C1 and C2 are very particular numbers. And then we went on to figure out what those were. And so this is true for particular values. Particular, this is my own G for general and P for particular is kind of my own lingo, just so that my notes make sense. If you have nothing there and you just say Y equals and Y equals, there's nothing wrong with that. It's fine. They're both true. Particular. Now, I want to give you one question here, one example that actually has kind of a, there's one slight curveball to these problems that I'd like to acquaint you with. Curveball, you play baseball, curveballs are hard to hit. One curveball. What about this problem? What if I said, I'm going to make this really quick. Y double prime, let's see, let's make it minus 6y prime plus 9 equals 0. Why is this one different? You should say, well, okay, I got this. The auxiliary equation that I'm going to end up with when I make my guesses. When you make your guess of y equals e to the rx, you end up with the auxiliary equation r squared, thanks to this, minus 6r, thanks to that, plus 9 equals 0. So that what I hope you gather fairly quickly is these are actually pretty easy when you get the hang of it. But then what happens when you solve this one? Something different happens here. What do you get for r this time? This one factor is pretty easy, so I'm not going to use the quadratic formula. Notice you only get one answer to it. Like usually you get two, right? But this time it actually happens to be repeated. Your book would say, hey, this is a repeated root. A root is an answer. A repeated zero, repeated answer, repeated root. So you should say, well, okay, great, fine. The general solution. It doesn't make any sense to say this, does it? C1 e to the rx plus C2 e to the rx. Do you agree with that? Because you could just add those together and then it would become C3 e to the rx. So it's like, it's kind of like there's not, what do you do with this? Does that make sense? Now you might think nothing, like you're done. So whatever, who cares? There's one answer. That's true. Like this is works. That's actually true. So saying y general just equals CE to the 3x. Good, correct. True.
So does that have to do with there not being any y in the third term?
Oh, I'm sorry. There is a y in the third term.
Oh, there's okay.
Thank you for noticing that. I'm sorry I left that off. That's very important, by the way.
Yeah, I was gonna ask
Yeah.
that. So if there wasn't a y, is that just r squared minus 6r?
Let's see. Yeah, that's exact. Let's see. Is that true? Is that what would happen? I actually don't think it would even work if you think about it, because remember, this whole idea hung on the fact that every single term had an e to the x in it. Remember how every one of them had an e to the rx in it?
Oh
So
yeah.
if that last term didn't have an e to the rx, does it make sense that would screw this up and it wouldn't work? So again, that's kind of an illustration of how kind of narrow these questions are without that y. Just one little thing. But again, the cool thing about this is this is what springs look like. That's what's kind of cool. So that should have been there. I apologize. I didn't mean for that to be confusing. So just recognizing that there's kind of no point in somehow writing those separately, as though there's two different answers. But I guess what should bother you is, doesn't this only have one constant? And so, what if somebody came along and said, y of 0 equals 8 and y prime of 0 equals 2 or something like that, and gave initial conditions? You might think, well, how are we supposed to, is there some way to do that? Or, because you might think, well, couldn't this happen with a spring sometimes? Like it just so happens that you get the same answer twice. True. Well, it turns out that if there is a repeated root, there actually is more to this answer. And this is what the more is. And again, you should say, well, that's not what you just said. Like you just wrote the same thing twice. I only did that for effect. It turns out if they're repeated, there is, if you will, kind of a second term to it. But you can get away with that term in front of the e to the 3x not being a constant. Notice that. That's kind of cool. This is actually not a constant anymore. It's not just a constant out there anymore. It's actually an x term now. Now your thought should be, first of all, number one, like, where did that come from? Like, how did you know to do that? And then the second thing would just be, does that actually work? I mean, let's check that. Let's just play with that for a second while you let it soak in. You know this is okay. That term is going to produce 0. But let's check the y equals C2x e to the 3x. Let's check that. Well, notice the derivative taking is much harder now. Why is the derivative? Because we're going to check this. We're going to plug it back in here and see if it equals 0. But why is it really a pain to take the derivative? You shall be able to answer that. Why is it a pain to take the derivative?
Because it's product rule now.
Product rule. So the derivative of C2x is C2 times e to the 3x left alone plus the C2x left alone times the derivative of e to the 3x. The derivative of e to the 3x is e to the 3x, but then multiplied by 3. So that's the product rule. And to make matters worse, I get to do it again, because I need a second derivative to plug it back into my original equation, don't I? Fortunately, the derivative of C2e to the 3x, we love plus signs with derivatives. Fortunately, that derivative isn't hard. The 3 just comes down front. Derivative of e to the 3x is e to the 3x. So I kind of don't have to do product rule for that. But then I do have to do product rule for this. So again, the derivative of 3c2x is 3c2 times e to the 3x left alone plus 3c2x left alone times the derivative of e to the 3x, which is e to the 3x times 3. And so this is going to turn into a 9. And you might notice these, before we go, kind of plug it in, these are actually like terms here. Those are the same. In other words, I can actually add them. If I have 3 of those plus 3 of those, then I have 6 of those. But then the other one I can't do that with because it's got an x e to the 3x, so I can't add those. Now again, you're more than welcome to factor a c2 e to the 3x out if you want. But now let's go actually do what we said, which is actually check this. So the original problem was y double prime minus 6y prime plus 9y equals 0. And so we're saying, really, does that actually work here? So y double prime, I guess I can just copy that in the interest of time. Minus 6 times y prime, which was c2e to the 3x plus 3c2e to the 3x. And then finally, plus 9y plus 9 times y. And y we said was c2x e to the 3x. And so we're saying question mark, is that really equal to 0? Almost incredulously, like that can't possibly be equal to 0, can it? But let's look at all the non-x terms. Like this term doesn't have an x, right? It's just 6c2. And there's another one. There's a non-x term. Did I leave one out? I feel like I left something off. Yeah, I left off this x. There's an x right there that I left out. It's supposed to be an x there, and I didn't put it in there. So notice, indeed, you have 6c2e to the 3x minus 6c2e to the 3x. And so, well, that went away. And then let's take a look at the x, the terms that actually have x in them. Well, here's 9 of these terms. And when I say 9, I mean c2x e to the 3x's. You have 9 of that junk. And then you have minus 18, because this is multiplied by minus 6, right? So you have 9 minus 18, and then plus 9. 9 plus 9 minus 18. Sure enough, check. That actually is equal to 0. Isn't that kind of weird?
So we haven't talked about where that x came from yet, have we?
No, I just gonna said, hey, look, it works.
Okay, I was like kind of thinking about it and got lost in the weeds for a second.
Yeah, so. And I'm actually kind of thinking to myself right now, let's see, do I want to go down that road? I got. I think I'll just mention something about it, but I'm looking at this. There's one other thing I want to do, and I think we're going to run out of time, but we sort of, in this case, we sort of found that y1 was e to the, c1 e to the 3x. But then we kind of thought, like, what about y2? Well, it's the same exact equation. So it's like there's not two different equations here, right? Where was it? Two separate ones that we added together. And so So the idea here is just what if instead of this second equation just being some other constant, which again sort of looks like, well, that's the same as the original. What if that C2 was not C2, but was just kind of some other function, was like a different function of X? Does that make sense? Like, does that number, does the thing in front of it always have to be a constant? That's just kind of the question. Like every time we just said, hey, look, a constant works, but the idea is, does it have to be a constant? Could it be something else other than a constant? Could it be some function of X, like sine of X or X or X squared or something like that? Could it be something more complicated? That's kind of the idea here. And in this case, and I think I'll give you this for extra credit if you want to try it. So for extra credit, go do this. Now we just did it a second ago where I threw an X in there. Does that make sense? I just said, oh, it's an X, and we noticed that it worked, but it's like, where did I even get that? Or how did I know to do that? And again, there, in my case, there could be two answers. Well, somebody told me, and then I just told you. Like, I don't know either. But this is where this logic came from. And this is not terribly hard. I would really recommend you do this. In other words, could you go do this? If that's what you're going to call y2, it's going to be some function of X. Well, we don't know what that function is yet. I just said, hey, it's X. And we're just saying, could it be something more complicated than just a constant? And so wouldn't you then have to go, you know, figure out the derivative of that statement? And notice, because of, I'll start it for you. Because of product rule, you'd say, well, I'd have to find the derivative of that function times e to the 3x left alone, plus the f of x function left alone. Again, I don't even know what it is yet. I'm just saying, well, let's just try to go looking for it. And then the derivative of e to the 3x is e to the 3x times 3. And so wouldn't that be the first derivative of it? And then wouldn't we also have to find the second derivative of it? And then the idea is then go back and do what we did here, like plug it back in and set it equal to 0. But then ask yourself the question, you know, would there be some f of x that would do that? Is there some way that that does not have to be just a constant? And it turns out that if it's repeated root, if it's a repeated root, then there is a function. And not only that, it's x. It's not x squared. It's not sine of x. There is functions that work. The only hint I will, or the only other thing I'll just kind of mention, because again, I would highly encourage you to do this, is notice if you have repeated roots, what happens in the quadratic formula? Like in our problem, we had r squared minus 6r plus 9 equals 0, right? And so if you put this in the quadratic formula, you say, okay, the quadratic formula says negative b plus or minus the square root of b squared minus 4 times a times c all over the top of 2 times a, right? But what happens in the case of repeated roots? What happens next in this problem? Well, the only way you get the same root, go ahead, somebody was going to say something.
Oh, well, everything under the radical becomes 0, so it's just one answer.
Yeah, that's why you get one answer, because the plus and minus ends up being plus or minus nothing. And so you end up with 6 plus nothing over 2, 6 minus nothing over 2. And so b squared, if you will, b squared actually equals 4ac. And so if this is true, if that's true in this particular case, then you can actually find a function of x that will actually work up there. And so again, I find that to be a brilliant question. And to be honest, I'm not smart enough to have asked that question. If I was solving this problem and I just got, you know, oh, look, it's the same answer twice, I would have just quit right here. Wouldn't you? Would many of you? I'm just going to quit right there. I'm done. That's good. Good enough. I'm fine. And is that true? Yep, it's true. But some really smart person, smarter than me, thought, does that number have to be a constant in front of our e to the 3x? Could it be some other function? And they went down this road, and the answer is yeah. If it's a repeated root, then it doesn't just have to be a constant. It could actually be a function. And not only that, this is what that function is. And so that's just brilliant, a brilliant idea. So I would highly recommend you follow that road. Now, anytime I ask extra credit questions, it isn't just like I said it and then lots of luck to you. Like if you take it on, don't quit till you get it. If I need to give you some hints, if you need to talk with me after class, then good, talk to me after class. I want you to understand it. I want you to get it. If I have to give you 5 hints and then you finally get it, good, extra credit for you. Don't quit unless you see it to the end. I think I gave a question like this, but we have just enough time, and this is why I had to hustle through that last thing instead of not just show it to you myself. What about this? What about a third order? Like this? What if I give you the third order differential equation, y triple prime minus y6 minus 6 double prime minus y prime plus 30y, don't forget the y this time, equals 0. Would that be possible to solve using the exact same logic of this?
I don't see why not. You would just have a cubic auxiliary equation.
Yeah, I mean, it actually isn't any different. Like, so we added a third derivative. Isn't e to the, 5x the derivative? That's still e to the 5x. And so the same, it turns out the same exact thing happens. In other words, you say, well, the answer is still e to the rx, and you're still going to get the same auxiliary equation, r cubed, thanks to this term, minus 6r squared, thanks to that term, minus r, thanks to this term, plus 30, thanks to that term, equals 0. So you get a cubic equation. Now you may remember cubic equations are horrible to solve. We don't have a cubic formula. And so we spend a lot of time in 111 floundering around with this sort of a thing. But if you actually had to solve this and you weren't stuck with anything, what you should understand is the only way to solve this is to factor it. And if we were lucky, it would actually have 3 answers, right? Like it might be, I don't know, r plus 2, r minus 7, r plus 9 or something like that. Then it would actually have 3 answers. Somebody tell me this, why is there no reason to check that 7 is, like 7's a dumb choice? Why would it not be 7?
Because nothing in there is 7 isn't a factor of anything in any of the numbers in there.
It's not so much any of the numbers, it's this number. Like, where does that come from? Doesn't it come from 2 times 7 times 9? Isn't that what the 30 would come from? So whatever those factors are, they're going to have to be like multiples of 30. Like, wouldn't 2 times 3 times 5 do it? Like, it could be 2, 3, and 5. Now, again, this is only if it's canned, and I was careful to make this up so that it came out as whole numbers. But what's the cheat way to solve this if you don't have any way of knowing, since you live in the world of technology?
Graph it.
Graph it. Yeah.
See what the x-intercepts are.
Yeah, the x-intercepts are where the zeros are. So if this crossed at 5, then you would say r minus 5 is the solution. That was the big takeaway from Math 111. Or you could just say, I'm going to try this right now. Hey Siri, solve r cubed minus 6r squared. She didn't like that. Hey Siri, solve x cubed minus 6x squared minus x plus 30 equals 0.
Here's what I found.
Isn't that awesome? I didn't think that would actually work, but it did. Oh my gosh, what a world we live in.
Do you have
So-
Open Alpha on your iPad, or did it go on the internet? And find
That's
it?
on my iPad. So my iPad's just a phone.
That's awesome.
So it crossed, if you graph this, it crossed at -2, which means, well, actually, I don't even need to do that. I mean, I'll go ahead and write it down. It means it would have factored to r plus 2 since it crossed at -2, and r minus 3 since it crossed at +3, and r minus 5 since it crossed at +5. Like, that's what it factored to. But again, the whole reason, the takeaway is that the r is -2, +3, and +5. That's all I ever really wanted to know, right? Hey Siri, solve the second. So let's try that again. Hey Siri, solve the third order linear homogeneous differential equation y triple prime minus 6y double prime minus y prime plus 30y equals 0.
I found this on the web.
That's more like it. I was gonna say
I didn't think it was gonna work.
I was gonna lose it.
If you gave that in terms of what it's with not the prime notation, but like the actual dy over
Right.
dx notation, might actually get it.
It might do it. But the funny thing is like by the time you guys are sitting in my chair teaching, that probably will be possible. The question is, do you need to know how much math do you actually need to know in our culture? I'm not going to belabor this point super long, but how much math do you actually need to know? Like I just showed you Siri answering 4 weeks of a Math 111 topic, and it just answered it. I mean, this is the modern day version of a calculator, isn't it? It's like, isn't that why you go to a calculator? Hey, I can't solve this, so I put it in the quadratic formula and solve it. I don't know what 27 times 19 is, so you go to a calculator. Is it any different to say, hey Siri, what's 23 times 19? It's not really any different. So, by the time you guys some of you are teachers, do you need to know how to solve third order linear differential equations if you can just ask Siri and it tells you the answer? Well, not if your goal is practical. So, I mean, I don't know. What are your thoughts on that?
Well, if Wolfram Alpha goes down, humanity declines.
And that's often the answer. Like that's, it's like, well, what if it doesn't work quite right? Or, what if the power goes out, that kind of a thing, which is true, but not super compelling. I don't know. Interesting, isn't it? Anyway.
It depends on how far you plan on going with math, I guess.
Yeah, and it depends what you're trying to accomplish. I mean, in the sense, if your goal is just to build your suspension system for your bike, and that's your actual goal, and your goal is to, make a living and make a cool bike, then, math is not that necessary if I can get it. But the problem is actually in the real world, it's not, no one's ever going to walk up to you and write that red equation down. Do you understand that? Except a math nerd. In the real world, you actually have to formulate that yourself. That's actually the hard part. It's not solving it. It's even noticing that a differential equation is what models a spring in the first place. And so, I mean, I actually don't have a great answer to this. It's certainly beautiful. I mean, I think it'd be a shame to just have to use technology to get every answer. It feels really cool for me to, be able to figure things out for myself. But, is it necessary for somebody that says they hate it and don't want to do it? It's like, that's harder and harder to make that argument.
I feel like they should be taught in a way that they don't hate it, then hate it, rather than just making them not do it.
Right. Yeah, it's pretty interesting, isn't it?
If you're smart enough to find the equation like what you're talking about, I feel like you're already smart enough to, solve it. Like finding the equation is the hardest part. Yeah,
finding the equation is actually the hardest part. Like modeling the real world with math is actually the hard part. Solving it is not the hard part. And if a person sort of chose to kind of, cheat, again, I say that in quotes, but then so much for them. As a more practical example, I just bought an electric mountain bike. What does that mean? That means I get to the top of the hill because of technology and not because of the strength of my legs. Is that cool? Well, yeah, in a sense, but is it also kind of a bummer? Is there a place for like a purist to say, I got here under my own power and you got up there using technology? It's like, that's an interesting argument in a lot of places in our culture.
I think I'd rather be able to solve a second order differential equation by hand than find the roots of a cubic equation. So I feel like I'd be okay with where I am right now mathematically with using technology for the roots, but not necessarily the differential equation. But if I'm doing like differential geometry or something, I don't really want to solve a differential equation by hand. So
I feel obligated to mention that we do have the cubic formula.
Right.
True. You're right.
It's just a bit of a pile.
Yeah, it's a horrible disaster, but it actually is. I'm glad you said that, Landon, because it is.
Well, and you can also, there's some method of looking at the last number and dividing by like some monomial expression and then getting a quadratic equation that you can then factor.
Yeah, and so notice they're actually, you can do this by hand, and you know, I'm old, but not ridiculously old. And in my day, we didn't have the ability to cheat on this. We didn't even have a graphing calculator to cheat and get the answer. So we looked at this statement here and said, well, it's going to factor to something like this. And we said, well, that's a 30. So this could be 1, 15, 3, 5, 6. Like those are the choices. And then we just guessed and checked until we found one that worked. The bummer is the only reason this worked is because I made it personally by starting with this, multiplying it out and getting that. In other words, if somebody's not nice and just makes up random coefficients up here, then these are all going to be ridiculous decimals. 2 times -3 times -5 really is 30, but isn't there also 3 decimals that could be there that also multiply to 30? The answer is yeah. Would you ever be able to guess them? No. So anyway, that's just, it's interesting. But notice actually just going out the door, like solving a third order differential equation actually isn't that much worse. You're still taking a guess. It's just you end up having to solve a cubed equation instead of a squared equation. We're not really as efficient at that. That's not the kind of question I'd probably put on a test, but it's worth being in a homework assignment. Notice the general solution has, all kinds of, has 3 unknowns, and incidentally, if I gave you initial conditions, I would have to say something like y of 0 equals 2, y prime of 0 equals 4, y double prime of 0 equals 9. It would actually have to have 3 initial conditions. You'd have to know the initial position, the initial speed, and the initial acceleration in order to solve this one, which is kind of interesting to think about. And again, that makes sense because if you have a third derivative, wouldn't you have to take 3 integrals, and wouldn't that produce 3 constants? So that's just kind of interesting to think about. Anyway, we're at 9:55, my machine says, so get yourselves out of here, and we're going to pick this discussion up tomorrow. Fortunately, we're going to be looking at the same thing tomorrow, but we're going to look at what happens if the number under the radical sign is a negative, an imaginary number, and crazy. And this is a really neat part of this class. You'd think, oh yeah, well, if whatever, there's an imaginary answer, but it turns out the imaginary answer is actually the one that models the spring, not the ones we did today. So we're just going to continue this discussion starting tomorrow. I'd highly recommend to that end that you do 4.2's assignment tonight, just so that your brain's along with it. All right. Adios.